Can you hear me now? Okay. All right, let's just do with this setup now. I think it's okay. Okay. So last class, we talked about the sparsitron algorithm, and we started discussing multivariate Gaussian distribution and PSD matrices. And so today, what I want to do is talk a little bit more about PSD matrices, what they are, and then discuss Gaussian graphical models, which was our original motivation for looking at these matrices in the first place. All right. Okay. So, and I should also say a couple of announcements. Assignment 3 is graded. And assignment 4 solutions are also up. And finally, remember that exam is next Wednesday at 8 a.m. Again, this is per the university schedule. All right. And the other thing to keep in mind is many of you are asking if you can have a cheat sheet for the exam. I mean, I really don't think it helps, and sometimes it might hurt to try and remember things as opposed to actually trying to understand stuff. But nevertheless, since many of you are asking, you are allowed a one-page single-sided sheet for the exam. Okay, but as I said, it's more important to kind of understand the concepts than to memorize stuff. But if it helps, it helps. So you can bring that along. Okay. All right. Okay. So last class we talked about PSD matrices. And so we said A, which is a symmetric matrix, is positive semi-definite or PSD if for all vectors V transpose AV is greater than or equal to 0. Okay. And we said covariance matrices of distributions are PSD. Okay. And a multivariate Gaussian distribution is parametrized just by the PSD matrix. Okay. And as notation, one important notation you'll see throughout is A is PSD is typically written as A is greater than or equal to 0. Again, the matrix world, this is the notation that is used. All right. And now let's look at some examples of PSD matrices. We saw one example last time, which was, okay, the matrix 1, -1, -1, 1 is positive semi-definite. It's greater than or equal to 0 in this PSD sense, right? What other matrices are PSD? So one way to arrive at PSD matrices is to actually think of what this equation should be, right? So we know that A is PSD if and only if for all vectors V transpose AV is greater than or equal to 0, right? So, if this is a quadratic function in the V's, right? So V transpose AV is summation ij Vi times Vj times Aij, okay? So if we define a quadratic function, which is always non-negative, then the corresponding matrix would be positive semi-definite, okay? Can you think of a simple quadratic function, maybe a 2 variables, 3 variables, which is always non-negative? Any suggestions? You can either chat it out or just unmute yourself and tell me. Let's see. Okay, so if there are no suggestions, here's one. So we can take the quadratic form, which is V1 minus, let's say, V2 minus V3 whole squared. Okay, so if I look at this function, this is V1 squared plus V2 squared plus V3 squared, minus 2V1 V2 minus 2V1 V3 plus 2V2 V3. And this by definition is always non-negative, right? So I can define a corresponding quadratic form now, which is 3 by 3, right? So I will put 1, 1, 1. V1, V2 is 2, so I'll put let me do some color coding. So this is minus 1, minus 1. Okay, so if I look at this matrix now, A, V transpose AV equals this expression, which we know is V1 minus V2 minus V3 whole squared. So this is always non-negative. Okay, that's one way to get it. And you can build things in this way. Like, and if I look at the quadratic form, V1 minus V2 whole squared plus V2 minus V3 whole squared. Now, this is also always non-negative. So I can then define a corresponding matrix which gives me this quadratic form. Okay, so there are many ways to get such positive semi-definite matrices, and these are some of them. Okay, any questions about this? In general, there is one category which I think is perhaps very important, and these are called Laplacian matrices. Okay, so given a graph G, we can define a matrix LG such that so for every edge in the graph, I'm adding the term Vi minus Vj whole squared, right? So by definition, for every V, you get V transpose LGV is greater than or equal to 0. So the corresponding matrix would be positive semi-definite. Okay. So for instance, if you do it here, so what is this guy? This is V1 squared plus V2 squared minus 2V1 V2 plus V2 squared plus V3 squared minus 2V2 V3. Okay, so let's make it into a matrix. I will get 1, here. So these two things add up to give me 2. And this gives me 1. This gives me -1, -1. And finally, this gives me -1, -1. Okay. Any questions about this? So this is just to say that, for any graph, there is an associated PSD matrix. Okay, so which is given by this expression. All right. So positive semi-definite matrices are everywhere. You can associate with them with graphs and so on. All right. Okay, those are some examples. But now let's go back to why we're looking at them, right? So for us, the most important property is that for every sigma, which is positive semi-definite, we have a multivariate Gaussian distribution. Okay. And in last class, we said that, if sigma is d by d, we can learn a good approximation to sigma from O of D samples. Okay. But in many cases, we don't think we have D samples. The dimension could be very huge. The number of data points is small, and we still want to do some kind of multivariate Gaussian distribution fitting or any other kind of distribution fitting. So what do we do in that case? And that's where Gaussian graphical models come in. And let me now talk about that. Okay. All right. 1 second. All right. So let's talk about learning Gaussian graphical models, and something that we're going to focus on is doing so without condition number bounds. So what does this mean? Where am I? Okay, so first I'll talk about what Gaussian graphical models are, what's the motivation, and then we'll say a very simple algorithm for it. And then I'll say a few words about when it works and how and why it works, okay? And the algorithm, really is basically in this bullet point here, and there's nothing beyond what's shown there, but hopefully that'll make sense in a little bit, okay? So what are Gaussian graphical models? And, in some sense, it's just a fancy word for a multivariate Gaussian distribution, right? So we said a multivariate Gaussian distribution is parameterized by n0 sigma. And here I'm switching notation slightly and talking about the dimension being P, which is kind of the standard statistics notation for it. And D will be the degree of the graph, as we'll see, okay? But, this notation change hopefully isn't too confusing. So P equals dimension or number of features. Okay, so think P is very, very big. Okay. And as I said, the Gaussian distribution, the formula is given by this, exponential and something, and this is the normalizing constant, but we said we don't care about the normalizing constant too much yet. All right. And now, if it's just a Gaussian distribution, why are you calling it Gaussian graphical model? Well, it makes sense when you look at a different thing to focus on. So instead of looking at the covariance matrix, which is what you usually focus on, we're going to focus or emphasize the precision matrix, which is the inverse of the covariance matrix. So let's assume that the covariance matrix is invertible. Otherwise, you can just take out the kernel or add some small perturbation. Let's not worry about such technicalities. But for any distribution, you can first compute its covariance matrix, and you can compute the inverse of the covariance matrix. And inverse of the covariance matrix has a name in statistics literature. It is called the precision matrix. And that is what we're going to focus on. Okay. So why focus on precision matrix? Because for Gaussian distributions, the precision matrix encodes conditional independent structure, just as we were talking about in the context of graphical models. Okay. In particular, let's say I have a Gaussian distribution with covariance matrix sigma, precision matrix theta. Then you can define a graph, which is the support of theta, meaning I add a graph where an edge is present between I and j if the corresponding entry theta ij is non-zero, right? So if theta ij is non-zero, I add an edge, otherwise there is no edge. So I build this graph, and the claim is that this is a dependency graph for the distribution X. Okay, so by looking at which entries are zero or non-zero in the precision matrix, I can build a dependency graph. And recall, dependency graph means that you have the Markov property. That is, whenever there is no edge, like here, there is no edge between 1 and 4, then 1 and 4 are independent, condition on the neighbors of one of the vertices. Right? So for instance, here, if I take 1 and 3, there is no edge between 1 and 3. So 1 and 3 should be independent, conditioned on the neighbors, which are 2 and 5. Okay. So this is how we define dependency graph and led to undirected graphical models. And what we're saying is for the Gaussian distribution, a very simple characterization of the dependency graph is you look at the precision matrix, look at the support of the precision matrix, that gives you a distribution. Okay. And so the reason, well, is a question. If the multivariate Gaussian covariance is identity, then we have a pointer. Is that correct? Yes, it is correct. In fact, there the dependency graph is completely empty, which makes total sense, right? Because all of the coordinates are independent of each other. And we'll say a very concrete example soon, and a very important example in practice too. Okay, but that's a good question. All right. So now, going back to where we were, so the reason we're talking about Gaussian graphical models is we parameterize these things by limiting the graphs that you observe, right? We said, if I want to learn the dependency structure, I need to assume something about the graph. And as in the case of learning Ising models, we are going to assume that the max degree of the graph is bounded. And as I said, there's some slight change in notation here, but hopefully that's not too confusing. So D equals degree of graph, P equals number of vertices slash number of features. Right? And we should assume that D is very, very small. Typically, we should think of D as being maybe 10, 3, and P is 10 to the 6 or 10 to the 7, so on. Okay. All right. And this assumption makes the formalism non-trivial and useful, right? So given that the degree is small, we are hoping that we can learn the Gaussian distribution in ways which is much better than general Gaussian distributions. All right. Okay. Can wonder why study this particular formalization? Well, as I said, Gaussian distribution is probably the most used distribution statistics, and GGMs are actually used very often in applied sciences for modeling statistical relations between variables, especially when you have very limited samples and you still want to learn the distribution, you want to make some assumptions, and this is one of the most commonly used assumptions. And they have many applications in machine learning and also in applied science. As I said, they're used to model gene-regulated networks or brain connection networks from fMRI and so on. And it's particularly relevant for these domains because there, the ambient dimension is usually really, really big, whereas the number of samples is much, much smaller. Okay. So the bigger picture, just to recall, is can we learn sparse dependency graphs from few samples, like learning Markov random fields and vector graphical models. And earlier we saw how to do this if you had discrete random variables, right? If you had random variables of 1 or -1, and you had 2 wise Markov random fields, we could do it via sparsitron, right? And today we're going to do something similar, or hoping to do something similar for GGMs, all right? And first, let me describe. Let's focus on a concrete example so that we have something in mind. So the example that I want to focus on is a random walk model. This is basically time series. So we have some time series data, right? And how is the time series data coming in? So time series data just means that your new random variable is your old random variable plus some random Gaussian noise. I'm calling it the random walk model because essentially, you're somewhere here, and then you go up or down depending on Zi. Okay. So formally, you have independent IID Gaussian random variables, Z1 through ZP, but each xi is a prefix sum of the first few z's. So x1 is z1, x2 is z1 plus z2, x3 is z1 plus z2 plus z3, and so on. Okay. And you can compute the covariance matrix of this Gaussian distribution corresponding to the xi's. Okay, so I can compute the Gaussian distribution corresponding to the xi's, and it looks something like this, right? So x1 has variance 1, x2 has variance 2, x3 is sum of 3 Gaussians, so it has variance 3, and so on. And the covariances also has this nice structure here, okay? So all of this seems nice, there's a nice distribution and so on, but what is the inverse of this matrix? What is the precision matrix of the covariance matrix? From the first time you look at the covariance matrix, it doesn't look like the precision matrix should be nice. But if you do compute it, you will notice that the precision matrix is actually very, very nice and structured. In particular, the precision matrix for the random walk model corresponds to this matrix. I just have 2's on the diagonal and -1's on the upper diagonal and -1's on the lower diagonal, and all of the entries are 0. Okay. So what do you notice about this precision matrix? It is extremely sparse. Each row or column has only 3 non-zero entries, and one of them is just the diagonal entry. So there are only 2 off-diagonal entries which are non-zero for each row or column. So given this, what do you think is the dependency graph of the distribution of the random walk model? Given the precision matrix, I can build the dependency graph, right? I add an edge whenever the corresponding theta ij entry is non-zero. So if I do that, what graph will I get? Any guesses? Exactly, linear path through all nodes, right? So the dependency graph is just the path graph, which makes perfect sense because the definition of the xi's is like a Markov chain. The new xi only depends on the old one plus some randomness. It doesn't depend on xi minus 2 and so on, right? So the graph that you actually get is exactly like this, right? And we saw for the Markov chain, the dependency graph is a path, and you have the conditional independence relations that you would expect. Okay, and you can see it formally here. So the covariance matrix as the left one, the precision matrix is the right one, and the dependency graph is in the middle. Okay. All right. So in the context of learning sparse GGMs, we're interested in two questions, just as we were for learning discrete GGM, discrete graphical models. One is structure learning. Can I learn the dependency graph? One is parameter learning. Can I actually learn an approximation to the covariance matrix or the precision matrix in some meaningful sense? Okay. And the structured learning means we're given samples x1 through xn from a GGM, and our output should be the dependency graph of the GGM. I don't know which nodes are actually present here. I look at the samples and somehow I need to infer, okay, this edge is present, this edge is present, this edge is not present, and so on. Okay, that's what we're trying to do. And the challenge, of course, as we've been emphasizing throughout, is that the number of samples you have is much less than the dimension. Okay. If you had a linear in the dimension many samples, you can learn any Gaussian distribution, even without assuming that the dependency graph is sparse, right? So we are assuming that the dependency graph is sparse, and that is the reason we expect to be able to do it. Okay. Any questions so far? All right. If not, so the structural learning question now is very concrete. Okay, there's a question. Intuitively, why does the precision matrix correspond to the conditional independent structure? It's a very good question. And part of the reason is basically, if you go back to the equation of the Gaussian distribution, you have this minus x transpose theta x here, right? So the distribution is proportional to minus x transpose theta x by 2. So I can write this as minus x, summation ij, xi times xj. Let me write it here. So this is exp of summation I comma j, xi times xj times theta ij. Okay. So you can see that in the exponent, you have this theta I just showing up. And now the reason is very similar to what happened in the discrete case. So recall the Hammersley-Clifford theorem, which gave us a characterization of dependency graphs and distributions. So you can fit that in here and kind of, that's one reason why the precision matrix encodes a conditional dependent structure. So anytime you have this kind of factorization, you get the corresponding dependent structure. Okay, hope that helps with the intuition at least a little bit. Okay. So the question that we are asking is, you're given n samples from a GGM whose degree is much less than the number of features. And can we learn the dependency graph with way less than the dimension many samples? And ideally, we would like the number of samples used to be logarithmic in the ambient dimension. Okay. And if we learn the dependency graph, that's the main difficulty. And once we do that, it is easy to learn the parameters afterward. So the crux and the main goal is to learn the parameters, learn the dependency graph, sorry. Okay. And ideally, we would want practical algorithms with provable guarantees. We want simple to implement, nice algorithms, which actually are guaranteed to work under whatever assumptions that you want to make, right? We want to quantify when does this algorithm work. Okay. So as a toy example to keep in mind, imagine you're trying to solve the following problem. You have an unknown order random walk, meaning the vertices are ordered in some way such that you have the same random walk example as before, right? So there's some unknown permutation pi, and they have independent random variables even to zp, and x pi of I is x pi of I minus 1 plus zi, right? It's the same structure as before, but just that the order It's not that x2 is x1 plus z1. Maybe x7 is x6 plus something and so on. Okay. So in this case, the covariance matrix itself will be somewhat jumbled. It doesn't have the same nice structure as it did before, but it's only because the rows and columns are permuted. You can permute them back to make it look like that, but you have something like this. Okay, this is the covariance matrix. You don't know the covariance matrix. You're only seeing samples from it, right? And you can compute the precision matrix. So the precision matrix of this particular covariance matrix is shown here. You can once again see it's a little bit more garbled. The rows and columns are permuted, but the underlying point is that this is still a sparse matrix. Each row or column only has few non-zeros per row. Okay. And the dependency graph is going to be a path graph once again, but it's a permuted path graph, right? So you can see it's a path, but the order is different. Okay. So now imagine you don't know the covariance matrix, you don't know the precision matrix, you don't know the dependency graph. You're just given samples from this xi. How many samples from X do I need to find the hidden permutation? Okay. So essentially we're asking, okay, imagine that someone gave me this gave me a time series data, and then things were permuted, right? How can I undo the permutation and go back to the original order of the time series data? Okay, this is just a toy example to keep in mind for testing our algorithms. Okay, all right. So let's see how to solve this and what is known about this problem so far, right? So there's been a ton of work on this problem, and so there are several software packages which are actually used in various applied sciences domains. These are called something called Glasso, Climb, Aclimb. And Glasso, which was introduced in 2008, is known to achieve logarithmic dependence on the dimension p, which is very good. So it's log b if the precision matrix satisfies some strong condition. Okay, so it does get the desired sample complexity, but it needs stronger assumptions on the precision matrix. The precision matrix needs to satisfy some condition called incoherence. I'm not even going to define what it is, but it's such a strong condition that it is violated even by the random walk example we just saw. Okay, so the random walk example is still hard for this particular software package. And there are other packages like Climb and Aclimb. They also have the same issue, right? You can learn them with some number of samples, but they need strong bounds, strong assumptions on the covariance matrix and the precision matrix. In particular, they need to assume these matrices are somehow well conditioned and so on. And all of these are violated by many examples, such as anything which has a random walk, any dependency graph which has in long paths will violate these assumptions. Okay. So in summary, the software packages which are used widely do not work if the matrix is not well conditioned. For example, like if the random walk matrix. Okay. And it's not just that the guarantees don't work, they actually fail empirically when you implement them. So before talking about what kind of algorithms we can design, let's take a step back, right? We want efficient algorithms. That's of course our main focus, but let's even try to understand what is possible information theoretically. Let's say I give you infinite amount of computing time, but I only told you that you get a small number of samples. What is the least number of samples you need to actually learn the dependency graph, irrespective of the runtime? Once we know what that is, maybe we can strive for something like that with an efficient algorithm. Okay. All right. Even this was only settled relatively recently, like 5 years ago. 5 years ago seems like a lot, but it's relatively recent given the amount of work that is being done on GGMs. Okay, so in 2018, it was shown, the following was shown. So to characterize what is possible information theoretically, we need to introduce a parameter called kappa, which is really it's a way to measure how significant is a correlation along a single edge. So recall, even when we're studying Ising models, we assumed that each non-zero edge was at least half in magnitude, right? We said we need to assume that there is a lower bound on how small a non-zero edge weight can be, right? So kappa is something similar. It's just that, you don't look at the absolute number. You look at the absolute number, kind of the ratio of the diagonal entries to the off-diagonal entries, right? So you look at how big is the off-diagonal entry for any non-zero edge, how big is any non-zero edge relative to how big the diagonal entries are. Okay. Does this make sense? So you're kind of still measuring how big is each non-zero entry in your precision matrix, but kind of measuring it relative to the corresponding diagonal entries. All right, so if absolute value of theta ij divided by the square root of theta I times theta jj. So that's called the pairwise correlation, or the kappa parameter of the precision matrix, right? And it kind of measures the signal in 2x2 submatrices. You're not looking at the whole matrix, just count how significant is the correlation along this single edge, right? And what they showed in 2018 is any distribution, any Gaussian graphical model can be learned, is identifiable with logarithmic in the dimension times the degree of the graph divided by kappa squared many samples. So this is amazing because you're saying the dependence, the ideal dependence on the sample complexity is linear in the degree, log in the dimension over kappa squared. You think of kappa as a small constant, like half or one or whatever, something like that. Okay. So in contrast, for Ising models, we had exponential dependence on the degree, right? So when we studied sparsitron, for Ising model, we had exponential dependence on the degree. And even though we did not prove it, I stated that that exponential dependence is actually necessary for Ising model. Whereas for GGMs, which are very similar, at least in kind of in spirit, right? You're getting samples from distribution, you're trying to learn a dependency graph. You can actually get information, theoretically at least, get linear dependence on the dimension, on the degree. Okay, linear dependence on the degree, log dependence on the dimension. For Ising models, you can, at best, you can get exponential dependence on the degree, log dependence on the dimension. Okay, any questions about this? So this is what I meant by saying, yeah, the kappa is outside the log. Yeah, definitely. Yeah. So like, this is one case, you might wonder, why are you doing so much better for Gaussian graphical models as opposed to Ising models? Part of the reason is that this precision matrix theta, it turns out to also be positive semi-definite. Again, this is one essential difference between Ising models and theta. Okay. Any other questions? Okay. All right. So, and for the, as I said, the pairwise correlation thing is fairly small. If you take the random walk example, it says that the random walk example, the kappa is half, the degree is 2. So information theoretically, you should be able to learn the random walk example, even if you don't know the order, with only log p many samples, right? So degree equals 2. kappa equals half implies if order unknown can learn it with Isn't that amazing that, you don't need to know if someone gave you time series data and you somehow jumbled up the order, you can recover the order with only log p many samples. Okay, so if you have 1,000 dimensions, then you basically need maybe 10 or 20 examples. If you have a million, you still need maybe 30 examples or something like that. Okay. All right. And there's also a lower bound that, you need this roughly log p or kappa squared. Again, this kappa is outside the log, many samples. There's also a lower bound. Okay. The only downside. So what's the fun? That's a very good question. Is there intuition for this? Let's see. Let me think if there's a simple intuition. The short answer is that actually there is no simple intuition. Part of it will, um, comes down to something deep in statistics that you can solve certain kinds of sparse linear regression problems, but it is a non-trivial mathematical result. And in terms of intuition, it comes down to the fact that, well, hopefully it'll become a little bit clearer later on. Okay, so hold on to that thought. I do agree that it's an amazing theorem. Okay, as good as this result is, there is one very critical downside to it. And the downside is that it only gives you some kind of an efficient algorithm. In the following sense, it says there is an algorithm to even recover the underlying graph, but the runtime of the algorithm is kind of terrible in terms of the degree. The runtime is p raised to the power d. Okay, so in a sense, what you're ending up doing in this algorithm is brute force search, right? So this is basically exhaustive search over neighborhoods. Okay, so it says information theoretically you can do significantly better d log p or kappa squared, but the runtime is p to the power of d. Okay, and this runtime is quite problematic even for moderate size instances. Like as I said, we assume the degree is 3 or 4 and p is like a billion. It's awful to run like cubic time, or if the degree is 10, then it's much, much worse. Okay. So the ideal challenge, the ideal algorithm now would be one which can learn the dependency graph with roughly the right sample complexity, d log p or kappa squared, but the runtime is a fixed polynomial in P, like p squared, p cubed. P cubed is already pushing it, but we don't want it to grow with the degree. That's the most important thing. Okay. And in a paper from 2018, we kind of answered this question for a large class of models, and I'll talk about that result next. Okay. And more than the exact result, I want to emphasize a very simple, greedy strategy for solving such problems. And it also kind of subsumes the guarantees of all of the previous works. Okay. All right. So that's the introduction to what GGMs are, what we're trying to do. And now let's dig into, how can we learn them? All right. Okay. So before describing the algorithm, I want to describe a special class of GGMs that the algorithm works for. These are special in that they're not like generic precision matrices, but they're still sufficiently useful because they occur reasonably often. Okay. The first class is attractive GGMs. Okay. And again, the term attractive comes from from physics, basically from ferromagnetism and so on. Basically, a GGM is attractive if all covariances are non-negative. Okay. The covariances are non-negative means any two random variables, they are positively correlated. Like in the random walk example, things are positively correlated. Okay. So any Gaussian graphical model where the covariances are all non-negative is called an attractive GGM. And basically, if sigma ij is greater than or equal to 0 for all I comma j, this implies that the off-diagonal entries in the precision matrix are less than or equal to 0. Okay, so recall theta is sigma inverse, right? So when you invert, the signs reverse. So in the precision matrix, what you have is that the diagonal entries will still be positive and the off-diagonal entries are non-negative. And here I should emphasize something, which is that sigma is PSD implies the precision matrix is PSD as well. Okay, so the inverse of any positive semi-definite matrix is always positive semi-definite. Okay. All right. And there are many examples of attractive GGMs. They arise in machine learning in the context of Gaussian processes. The example of random walk that we saw is attractive because you can remember the precision matrix. All of the off-diagonal entries are 0 or -1, right? So they're definitely non-positive, okay? And they can be ill-conditioned. So these are hard to learn for existing algorithms before our work, okay? And what we show is that there is a simple algorithm called greedy prune, which we'll describe, and it learns attractive models with the right sample complexity, and the runtime is quadratic. So instead of running in time d, like, the dimension raised to the power degree, you're running in time which is quadratic, okay? There's a more general class called walk-summable matrices, but, let me not talk about that. And then talk mainly about the theorem, okay? Mainly about the algorithm and its analysis. All right. So how can we learn Gaussian graphical models? And so recall our problem setup. We are given samples from a GGM X, from a sparse GGM, and we want to learn the dependency graph of the distribution X. And the algorithm, just as we did for sparsitron, recovers a neighborhood of each vertex in parallel, okay? So you fix a vertex, try to learn the neighbors of that vertex, and then move on to other vertices. Okay, so just as we did for sparsitron, you focus on one vertex, try to learn its edges, and then do this in parallel for all of the other vertices. Okay, and the way we learn the neighborhood is as follows. We first grow a candidate neighborhood and then prune out some vertices. We don't know what the exact neighbors are. We'll grow a candidate neighborhood. Maybe we added some spurious ones. We'll then throw out some vertices, okay? So how can I grow a neighborhood? So we are getting samples from a sparse GGMX, and our goal is to learn the neighborhood of a single vertex, let's say a vertex 1. Any suggestions on how to add or, kind of which vertices to add as potential neighbors to vertex 1? And it's a bit much to think, right? You might say, okay, I need to figure out what are the potential neighbors to what, which vertex are connected to vertex 1. So what might you first try? Well, you can try to say, maybe I'll add the thing that is most correlated with vertex 1, maybe something which is most correlated condition on the individual variances or something like that, right? But it turns out the best way to do it is to do it in a greedy way in the following sense. So I'll start with an empty set as in set of neighbors for vertex 1. I don't know where the vertices are, so I'll start with the empty set. And while I haven't added too many vertices, okay, while the set S is small, I am going to do the following. I'm going to pick a vertex J that gives me the most bang per buck in terms of reducing the variance in X1 given that vertex's value. Okay, so this is saying find the vertex J which explains away the most of my variance. So I am X1. If I know the value at vertex 2, will that reduce my variance? If it doesn't, then I don't care about it. If I know the value at vertex 3, does that reduce my variance? If it does, I try to start taking it into account. Among all such vertices, I pick the one which reduces my variance the most. Okay. So intuitively, I think it makes sense. You're just saying variance of X1 given, like in step 1, that S equals 5, find which of these is the least. Whatever is least will get added to the set S first. Okay. Does that make sense? So for example, if the same value is repeated twice, then conditioning on that will make my variance 0, right? As small as possible, so I would definitely add. Okay. So that's our simple greedy rule. We have to still discuss how to implement it, why samples, but let's push that under the rug for now and just focus on this sort of clean picture. While given the current set of vertices, I decide I will add the vertex which gives me the most bang per buck in terms of reducing the variance of X1. Okay. I pick this index J and add it to my set and repeat until I hit a certain size limit, which I decide ahead of time. Okay. Any questions? All right, if there are no questions, that's an excellent question. We'll talk about that in a little bit. First, but let me describe the algorithm, and then we'll ask, how do you know that the greedy algorithm actually works? Okay. All right. So, the next phase is pruning a neighborhood. Okay. So pruning a neighborhood means, we added a bunch of vertices. Maybe we could have added some spurious ones. So at the end, we do some cleanup. We throw away vertices which are somehow unnecessary, meaning if dropping a vertex does not hurt me too much, meaning it does not change the conditional variance too much, I just drop it. If it is not giving me enough of a bang per buck in the end, I just drop it. Okay, there is some threshold tau, which is kind of a hyperparameter that you have to decide. And if dropping the vertex J, doesn't increase my conditional variance too much, then I just drop it. Okay, I do this again and again. At some point, I'll reach a steady state where dropping even a single one will give me a big drop in conditional variance. I don't do that. Okay, so that's the whole algorithm. You add things in a greedy way, and then we drop things. So there's a question, why do we want to minimize variance? So that's a good question. So there's a half answer to it. The half answer is what you're really looking for is some kind of quantitatively, it is hard to justify, but let me give you a qualitative justification, right? So why is looking for minimizing variance the right way, right? Oops. Okay, the intuition is something like this. Okay, so imagine, just as a toy example, imagine I have x1, x1, x1. Actually, Okay, hold on. Okay, so imagine I have three variables, and the first one is x1, the second one is the same one repeated, and the third one is completely independent. Okay, let me call it x3, right? I have the x2 equals x1, so they're completely correlated, and the third one is independent, all right? Now, what is the conditional variance of x1 given x2? If I give you x2, what does it tell me about x1? It's fixed. So the conditional variance is 0, right? On the other hand, variance of x1 given x3 is high because they are independent. Okay. So at least qualitatively, it's saying that somehow if x2 is contains a lot of information about me, then conditioning on x2, my variance should decrease. Okay, so it's a little bit like saying, if you have a specific gene, suppose that you're more likely to have a disease. Then once a condition on you having that gene, the likelihood, whether or not you have the disease, the variance would decrease, right? And that's the qualitative thing we're exploiting. And there are a couple of questions. The first one is, does variance of x1 given x3 equal variance of x1? In this example, that's exactly what happened. Because x1 and x3 are independent, conditioning on an independent thing doesn't change the variance at all. Okay. And as I said, this is just kind of a qualitative explanation. Making it quantitatively work, of course, requires work. All right. And we'll see a partial explanation of it in a little bit. And there's another question, why wouldn't you check if the variance reduces by 1 plus tau in the growing phase and break if no variable reduces the variance? That's again definitely possible. You can also do it that way. We found that empirically and for actually analyzing things, this is easier. Okay, but your suggestion is definitely something that you can do too. And I'm pretty sure that'll work. But I think implementing it is maybe a little bit more cumbersome. Okay, does it make sense, Arush? Okay. So, all right. So now the algorithm is completely, specified, right? You just add things to in this greedy way up to some size, and then you throw out some things. Okay. And as I said, even the case of a simple random walk is surprisingly hard for existing packages, right? And you can make it a little bit trickier by considering a following simple challenge. The precision matrix is a path, and then you have a bunch of small isolated 4x4 cliques. Okay, the max degree here is 3. So these 4 form a cluster which are completely independent of everything else in the graph. So these 4 are independent of all of the other random variables. And same for these 4, and these 4. So let's say you have 1 million of these, half of them are in this path, and the others are in this way. Okay. And so the precision matrix of this graph, when you generate things in this way, looks like this. Orange means 0. So there is a path, kind of strip along the diagonal, which is non-zero, and everything else is 0. It's a very simple looking precision matrix, right? So there are 3 off diagonal entries which are non-zero. These cliques are shown here. And then this is just a path. Okay. And you can change the intensity along these edges, and so on. That's another parameter that you can tweak. Okay, and that's kind of shown in this sort of semi-heat map here. All right, is the experimental setup clear? Let's just run. Can we learn this particular GGM from samples? What happens if I do it? Okay. And this is what happens. Okay. So you run the other algorithms and the greedy algorithm, and you can see the greedy algorithm is like, remarkably accurate. It matches the true precision matrix almost exactly, whereas the other ones have a lot of, spurious edges. Okay. It might not seem like, the spurious edges are that frequent, but given that, each vertex is supposed to be connected to three things, if you have six edges, that's a big, it's not very good estimate. Okay. Whereas the greedy thing really does well. All right. Does the setup satisfy the constraints of Glasser? It actually does not, because remember, as we said, whenever you have the path, which which I think is a very important, which can arise in practice anywhere. And anytime you have a long sequence of things, Glasser's conditions fail. It doesn't allow you, if you have any sort of long chain, it doesn't have to be a complete path, but even if some piece of it is there, the conditions fail. And this kind of shows that, it's not just a shortcoming of our analysis. We can't just do a better proof. We have to change the algorithm. Okay. All right. So, and you can also check what happens, not just in terms of this plot, you can check the recovery rate, how many samples do you need to actually learn the graph? And in all of these cases, greedy prune does very well. Right? Every algorithm kind of gets beaten by greedy prune more or less. Okay. I can tell you more about these plots and so on if you're interested, but the summary is that essentially changing the edge weights, greedy prune is consistently performing well, whereas all other algorithms fail in one setting or the other. Okay. All right. So greedy prune learns attractive models with nearly the right sample complexity and quadratic runtime. That's a theorem we did not prove. And it actually learns a much bigger class of matrices called walk-summable matrices with almost the same kind of, getting close to the information theoretical optimal sample complexity, but kind of off in this dependence on kappa and the degree, but the runtime is still very good. Okay. And, as I said, it is empirically better. We actually have a package where people in statistics and applied sciences actually use R a lot. So we released an R package for this algorithm that people can download and use. Okay. And even though we've been focusing on Gaussian distributions, you actually don't need your underlying distribution to be Gaussian. The guarantees work as long as the precision matrix satisfies the conditions we are looking for. As long as the inverse of the covariance matrix satisfies the conditions that we had for Gaussian, the algorithm still works. The interpretation is not accurate, but the learning part and everything else works. Okay. So in the remaining few minutes, let me say a few words about the analysis. Okay. All right. And for the analysis, I'm going to go to the slides again. Okay, and the main theorems that we had were greedy prune learns attractive GGMs with right sample complexity, and quadratic runtime. Right? So let me say a few words about this quadratic runtime. So what's the algorithm, right? So recall right? So this is the entire algorithm, and we do this in parallel for all of the vertices, right? And doing a single step of this to estimate this variance. When you have samples, you cannot estimate this variance exactly, but you can get an approximation of this variance, okay? And you can approximate it by standard tools in statistics. Okay, you can estimate conditional variances essentially by solving a limited least squares regression problem. And the runtime here is O of size of S. Right? As long as the size of S isn't too big, you can do some least squares regression to figure out what is the conditional variance. And since this minimum takes, you have to look at D things. For each vertex, you have to, for each vertex, you have to do for each vertex, the runtime is roughly or degree squared times dimension. Okay. So the total runtime, since you do this in parallel for all of the vertices, becomes quadratic in the number of vertices. Okay, and we think of degree as being a small number, so the main emphasis is on the dimension dependence. Okay. And there's a question, is it possible that one vertex may have assigned a neighbor, but its neighbor has pruned away said vertex? It is possible, but given the theoretical guarantees that we show that you will recover the entire graph exactly, it's not going to happen. I mean, just in terms of the algorithm specification, it is possible, but it won't happen as long as the conditions that we have are holding. And if not, you can probably symmetrize and say you add the edge, even if one of them says the edge is present and so on. Okay. And one other thing I should say is in our paper, we had this condition that we didn't talk about called walk-summable matrices. It's a much larger class of covariance matrices, but it's still somewhat restrictive, and we weren't sure how frequent it is, but we looked at some kind of common graphs like it coming from FM gene regulatory networks and so on. And we found that they were very close to satisfying the conditions that we had, that they were almost walk-summable and so on. Okay, so the conditions are constrained, but still not that. Okay. All right. So let me say a few words about this theorem. The other part saying that unit also works for the much general class of walk-summable matrices is much more complicated. And it involves some non-trivial properties about graphs and effective resistances and so on. But I think there's a nicer principle that kind of an age-old principle underlying the success of greedy prune for attractive GGMs. And I think this is something that is worth knowing for its own sake. Okay. All right. So why does greedy work? So has anyone of you seen greedy algorithms before? Can you think of some problems where greedy algorithms are known to work? Have you seen examples of greedy algorithms where they're provably known to find the best solution? Maybe in your algorithms class or something like that, you might have done some greedy algorithms. Are there instances where it's known to work? Interval scheduling is one. Min spanning tree is one. Shortest path is another. And there are many, many examples. Okay. And in fact, there is some underlying meta principle or kind of one nice setting in which greedy algorithms are known to always work. Okay. And to describe that setup, let me say the following. So we're using the pretext of GTMs to really do something just kind of a classical algorithms question, okay? So imagine I have a function on subsets of some universe, right? Let me write it as set n to real numbers. Okay, so this is all subset. And our goal is to find argmin. Okay, so I have a function on subsets, and let's say f is decreasing, meaning if if s is smaller than t, then f of s is greater than or equal to f of t, right? So it's kind of decreasing as a function of subset, and you're trying to find the set which minimizes the function subject to a size constraint. Every time you pick an element, let's say you have to pay $1, you get to pick t elements. What is the least value you can get? Okay. And the example that is relevant for us is the following. So recall in greedy prune algorithm, what were we doing, right? So we were looking at the conditional variance function. Okay. So in a sense, we were trying to find S subset of n minus 1, or let's say actually 2 through n, that such that what is the minimum value? Can you, well, the minimum value is, the minimum value need not be 0, but at some point it stops changing. Right? I shouldn't say what's the minimum value, but basically what's the argument, right? And you have 1 and it has some number of neighbors. Let's say it's connected to 2, 5, 7, 8. Now, if I have other connections, because of the graphical model structure, once I know the neighbors, conditioning on this is irrelevant, right? So if I have 2, 5, 7, 8, and maybe this is 10, then because of the graphical model structure, the variance of x1 given x2, x5, x7, x8 is the same as variance of x1 given x2, x5, x7, x8, comma, x10, right? So adding these other things is not going to help me decrease the variance once I add all of the neighbors. Okay, so that's the intuition behind why we are looking at minimizing the conditional variance. That's kind of another intuition from that. Okay. And if you find the set S with whose size is close to the degree and minimizes the conditional variance, then presumably I have found all of the neighbors. Okay, so that's the intuition. So in some sense, let's say we accept that intuition and that is our algorithmic goal. I can define a function now. F of S is variance of x1 conditioned on xs, right? And S is subset of 2 through n minus 1. Okay. So as a proxy to learning the neighbors of 1, we are trying to solve t is some bound. It doesn't have to exactly be the degree. Even if you're slightly worse or slightly good, we are okay. Okay. Does this make sense intuitively? Like, I want to find the set of neighbors. So I'll try to find the subset which minimizes the conditional variance subject to the size. Okay. And the intuition is that if I pick out the neighbors, then adding anything else is completely, useless. All right. Okay. Now, what can you tell me about this conditional variance function? Okay. Maybe let me change notation and call it, oops. Let me call it, no, let's keep F, it's okay. Why complicate things? Okay. So what can you tell me? Can you tell me some properties of this function F in general? Any properties of F you can think of? Is it positive, non-negative? The most important thing is, as is already one of the important things that's already pointed out in the chat is F is decreasing as we add vertices. Okay. It is decreasing as we add vertices. And it is non-negative, but that's not as useful as just saying that it is decreasing as we add vertices. Okay. And in general, we can go back to this question. We have some, we know a lot more about our function f, but we can ask, okay, do I really need to use all of the information? What if I just have something like this? Can I optimize this? Is there a way to solve this particular goal? Okay. And for any such set optimization function, you can define the greedy algorithm. So whether or not it works in general, anytime I have to minimize, I have a task which looks like this. I have a function on sets which is decreasing. As I add more elements, the value decreases, and I need to add the fewest number of elements. Okay. What can I do? And I'll start with the empty set and follow the greedy strategy. Okay, this is an age-old algorithm for optimizing functions on sets. Okay, right. I mean, there's a very good question here, which is our variance estimates are noisy. That is definitely true, and I'm pushing that under the rug. And if you look at the actual proof, that makes it somewhat annoying, but you can manage that difficulty by essentially arguing that our variance estimates are close enough to make the algorithm work. Okay. So for now, as a first cut, let's assume that we are actually working with the exact estimates. Okay. When you don't have the exact estimates and you have noisy, that's definitely involves extra work. We need to do some many calculations, some large deviation bounds, and so on to make it work. Okay, that's a good question. So anytime I have a set optimization function subject to the size constraint, I can try this age-old greedy algorithm. If you think of interval scheduling, you can set it up in this way. If you think of minimum spanning trees, you can set it up this way. And many other functions can be set up in this language. Okay. But in general, if I just do greedy, you're not going to find the optimal solution. In fact, you might be very, very far from being optimal. Okay. But there is one very nice and important special class of functions where the greedy algorithm will provably work. Okay. And this is the class of submodular functions. I should say supermodular because we're doing minimization. Okay. So what are supermodular functions? Let me pull up the exact notation that I had in mind. So there's a special class of functions where greedy always works. And this is the class of supermodular functions, meaning, so which functions are supermodular? So recall that f is decreasing, right? So meaning if I take any set S and I look at the value of S with something added, then which is higher? The smaller set, the value is higher, right? So we know that this difference is greater than or equal to 0. So f of s is bigger than or equal to f of s union j. And the same thing for any set T. Okay. So supermodularity just tells you that adding an element on a smaller set gives you more value than adding an element to a bigger set. Okay, it's kind of some kind of diminishing returns, right? It's basically like saying if your value of the function is low, then adding an element can, if you're starting with a small set, adding an element can change your value a lot more than if you're already have many, many elements. Okay, intuitively, does it make sense? If I have 1,000 elements and I add a new thing, the change is smaller than if I have a single element and I add a new thing. Okay, so supermodularity allows you to compare these differences. It's kind of a second order information. It's not just comparing S to T or S to S union J, but the relative improvement you get on big versus small sets. F is supermodular. And there's a flip side to it, which is submodular, where you flip all of the inequalities. If you have an increasing function, then the corresponding thing is called submodular functions, which are being used in machine learning and many other places again and again. S is subset of T. Then how much change you see on S when you add the element J is more than the change you see when I add the element J to T, right? So in text, adding an element makes a bigger difference to smaller sets. Okay, does the definition make sense? Okay, and a classical result, like, it predates even algorithms in the first place, goes back to operation research and so on, like during 1940s and so on, is that F is supermodular implies greedy. So if I'm trying to minimize a function values subject to the size constraint, a natural algorithm, as we said, is a greedy algorithm. And there's a blanket statement saying that for any supermodular function, the greedy algorithm will actually work. Is guaranteed to do as well as the best solution. Okay, this makes sense. It's a very strong theorem, and it's not actually that hard to show, just in terms of the amount of utility you get out of it. But it is well known, and the supermodularity or submodularity kind of are very nice because of this property that you can optimize them with greedy algorithms. Okay, any questions about this definition? I think it's a very nice and important concept that hopefully you'll get to see elsewhere as well. All right, so we went from GGMs to talk about discrete optimization to optimizing set functions and so on. So where does all of this tie in? The tie-in comes from the following. If X is coming from an attractive GGM, right? Imagine I have X, which is sampled from a multivariate Gaussian, where all of the covariances are non-negative, meaning it's coming from an attractive GGM. Okay. Then if I define f of s as variance of x1 condition on xs for all s subset of 2 through n is supermodular. Okay, so the conditional variance functions for attractive GGMs are actually supermodular. So if they are supermodular, then we know greedy algorithm works, and that's exactly what greedy prune is doing. Okay, so implies greedy algorithm works for minimizing conditional variance subject to size constraint. Okay, so this is a theorem that we are not going to show, but you combine this with this other result, which also we didn't show, but kind of very classical result in optimization. The next one is less classical. You combine these two, you get the result that I mentioned, that the greedy algorithm works for attractive GGMs. Okay. And you have to still track all of the parameters and so on. And you might wonder, none of this seems to require the pruning phase. Why do you require the pruning phase? And that goes back to this question that is asked in the chat, which is, our variance estimates are noisy. You don't have exact variance estimates, so they're a little bit noise. And to kind of correct from that, that's one reason why you have to do pruning. Okay. Any questions about the overall picture? Like, you have a simple greedy algorithm. We know that for attractive GGMs, the conditional variance function is supermodular. So greedy works, and kind of those two put together, say the greedy prune algorithm will work for attractive GGMs. And for the more general case, you have to go beyond supermodularity. And those things are not supermodular, but you can still make, there's a very different analysis which works. Okay. All right. So let me stop with that for the discussion on GGMs. And let me mention a few open problems and few remarks, really. Okay. So we still don't know the big open problem is to design an efficient algorithm which can learn any sparse GGM. Like, the greedy algorithm works for attractive GGMs. It's known to for Vox-mobile GGMs, but there are sparse GGMs where greedy prune fails. So greedy prune is currently the most broadly applicable algorithm, but even that fails for some specific sparse GGMs. And there we don't have any, so we don't have any general algorithms. And this is something that is, I think, a very important problem in statistics. And any work progress on that would be great. Okay. So that's all I wanted to say about GGMs and many other things. And in graphical models in general, we only barely scratched the surface. We looked at learning GGMs or Ising models. We didn't touch upon other things like what happens if you have noise in the data. There's something completely under the rug right now. There are algorithms for handling that. What if you have missing variables? What if you have latent variables? That's a very important problem in phylogeny, where you have to learn hidden Markov models, meaning there are some features which are actually underlying but are missing. You don't see them. Can you learn those things? So all of those are very important research problems and even practical important questions which we are not touching upon. Okay. So that's all I wanted to say about Markov random fields and everything else. And hopefully you learned, enough good algorithms to take with you for, wherever you see some machine learning stuff later on. And I'll see you next week for the exam. Okay? All right. If there are no other questions, let me end here. And remember, the exam is next week on Wednesday. Okay? Just a quick, sure, thanks. So go ahead, Neil, what's the question? Yeah, so for the exam, there is a cheat sheet allowed, but I strongly encourage you to kind of, write what you want, but, don't plan to rely on it too much. Okay? Hopefully that helps. So it's one-sided and try to not write it in very small print. Okay. Thanks, everyone. It was a very fun class, and hopefully I'll see you soon in other classes. All right. Bye.